This is a parabola, the shape created when you graph a standard quadratic equation. As the curve sweeps downwards, it crosses the horizontal x-axis at two distinct points. These two intersections represent the two valid solutions for the equation. While this is basic algebra today, for thousands of years, mathematicians focused entirely on just one of these points. In an equation like x squared plus 26x equals 27, ancient scholars easily found that x equals 1, but the other answer, negative 27, remained invisible to them. This wasn't a lack of intelligence, but a difference in perspective. Early mathematics was used to measure things in the real world: lengths, areas, and volumes. Since you cannot have a square with a side length of negative 27, negative answers were often ignored as nonsensical. By treating math as a physical description of the world, these scholars were limited to the solutions they could actually see or build. To these mathematicians, algebraic terms weren't symbols on a page, they were literal physical shapes. We can see this in how they solved x squared plus 26x equals 27. The x squared term was visualized as a literal square with sides of length x. The 26x term was a rectangle with one side of 26 and the other of x. Together, the area of the square and the rectangle added up to 27. To find x, they would split the 26x rectangle in half and move the two 13x pieces to the sides of the square. This created a new, larger shape that was almost a perfect square, except for one missing corner. That missing corner is a 13 by 13 square. By adding this area of 169 to both sides of the equation, the shape becomes a complete square with a total area of 196. Since the area is 196, the side length of this large square must be 14. Because that side is made of the original x plus the new 13, we know that x must be 1. This method is highly effective for finding positive solutions, but it cannot find the second answer. There is no way to draw or visualize a square with a side length of negative 27. Relying on geometry meant that any solution that couldn't exist in the physical world was simply left undiscovered. To find that second point, math had to move away from physical shapes and toward abstract rules. This starts with standard form: ax squared plus bx plus c equals 0. Instead of drawing squares, we can use factoring. We look for two numbers that multiply to give us the value of c and add to give us the value of b. Take x squared plus 5x plus 6 equals 0. Since 2 times 3 is 6 and 2 plus 3 is 5, we can rewrite the equation as x plus 2 times x plus 3 equals 0. This creates two paths. For the result to be 0, either x plus 2 is 0 or x plus 3 is 0. This gives us two solutions, negative 2 and negative 3. By moving from physical drawings to algebraic rules, the negative solutions that were once impossible to visualize become obvious. Factoring works well when the numbers are whole and simple, but it's difficult to apply when the coefficients are decimals or complex fractions. For those cases, we use the quadratic formula. It is a universal tool that works for every quadratic equation, regardless of the numbers involved. The process is purely algorithmic. You identify the values for a, b, and c from the standard form and plug them directly into the formula. The plus or minus symbol in the middle is the most important part of the calculation. It splits the formula into two separate paths. This symbol ensures that you calculate the result twice, once with addition and once with subtraction, which forces both solutions to appear. This method provides the correct answers even when they are impossible to visualize, allowing for solutions that geometry could never reach. This brings us back to the parabola and those 2 points where the curve crosses the x-axis. These two intersections aren't just mathematical leftovers. They represent a duality within the equation itself, a reality that was always there, even when our physical tools couldn't measure it. The evolution of the quadratic equation is the story of math moving from the concrete to the abstract. By moving beyond what we could draw in the dirt, we discovered how to solve problems that don't have a physical counterpart. It suggests that to see the whole picture, we sometimes have to trust the logic of the numbers over the intuition of our eyes.